Okay, so thanks for staying, actually. My name is Jakub, and this is a joint work with Boulder and Allan Zhang on one possibility how to integrate bounded rationality into correlated equilibrium. And correlated equilibrium has been around for almost 50 years now, I guess. So it's been studied under many different conditions in many different situations. But quite surprisingly, bounded rationality is not one of them. So, and before I get to the reason why I think it is so, and how we did it, let me just briefly start with explaining the framework of games we work with. Because in contrast to the previous two talks, our work is domain independent, which means that it can be applied to any normal form game. And I believe that most of you are familiar with normal form games, but just in case you don't know what it is, this is a structure which consists of players, their actions, and their utilities, where the utilities simply take any combination of actions, one action per player, and assign the players their utilities. In case we have just two players, then the game can be, any game with two players can be easily and conveniently visualized using those game matrices like you can see here, where rows and columns are just actions. Then in each cell, you can see the utilities of the first and the second player, respectively. And okay, so this is a special example, and I will be using this example throughout the whole presentation. So whenever you will just see some equilibria, they always refer to this example. And then we have mixed strategies, which are just probability distributions over the actions, and sometimes then they can be conditioned on some external observations, for example. Okay, so most traditional solution concepts assume that players just maximize their expected utilities, and they use the mixed strategies to do so. Quantal response is a model of bounded rationality which assumes, it tries to somehow reasonably relax this assumption. So instead of just maximizing, it assumes that human players make mistakes, but we can still somehow assume that action probabilities positively relate to the action probability, to the action expected utilities. And you'll probably hear much more about different kinds of quantal response models in the following talk. But in this work, we just work with generalized Lucent models, which are quantal response models which assume that every player has a specific function called Q, which we call the quantal generator. And then they play distributions which look like this, which basically is just the generator applied to expected utility, which is being normalized across all the actions to have a valid strategy. And then the quantal response equilibrium is just a fixed point of the dynamic when the players quantal respond to others. Okay, so how do we actually integrate quantal response, this model of behavior, into correlated equilibrium? Well, correlated equilibrium is a solution concept which is usually studied in its canonical representation, which assumes that there exists some trusted mediator which sends private single actions to the players according to some public distribution over action profiles. So for example, here you can see the canonical correlated equilibrium, which is the polytope inside the simplex of action profile distributions. And using this specific representation of canonical correlated equilibrium, this solution concept can be computed in polynomial time. But the problem is that using this representation, it is difficult to integrate any model of stochastic response like quantal response, because in quantal response we assume that everyone responds stochastically, but here the device just sends single actions. So there's a question, how would we even interpret this? So instead of using this canonical representation, instead, we use standard construction as introduced originally by Allan, which assumes that instead of sending actions, we have a device which sends just some generic signals. And then the correlated equilibrium consists of the signal distribution and a solution in the extended game where players receive their signals and then they act accordingly. And for the quantal correlated equilibrium, which we studied, the inner solution is exactly the quantal response equilibrium I talked about like 2 slides before. So we can assume that when we are given some generators, quantal generators of actions, then we can just define some expected utility, for example, this way, and then we just want that the make strategies of the players, which are conditions on signals, conform with the definition of the quantal response. So then here you can see an example of the dynamic, of the quantal response dynamic, where we can see one quantal response equilibrium and 2 quantal correlated equilibria, and because they are fixed points, and this is a dynamic, you can find the equilibrium where the curve crosses the quadrant's axis. And you can see that there's a distinction between the quantal correlated equilibrium and the quantal response equilibrium. Okay, so when we had the definition of quantal correlated, we asked some natural questions about this concept. And fortunately, it seems that it conforms quite well with some natural intuitive properties we would expect from this kind of equilibrium. So for example, when you take any quantal response equilibrium, you can easily extend it, this kind of equilibrium into quantal correlated equilibrium. Or when you take a sequence of quantal response functions which approach best response, then in case there exists a limit of the quantal correlated equilibria, then this limit is a correlated equilibrium. Then we were also interested in the set of correlated equilibria. It's a trivial compact, and then when we take a look at the correspondence between the signaling distributions and the corresponding quantal correlated equilibria, this is upper hemicontinuous. And as a consequence, in case we have unique quantal correlated equilibria for any signal distribution, then the set is also connected. Unfortunately, it seems that in most cases, the set is not convex, which may cause some problems when we want to optimize over quantal correlated equilibrium. And actually, you may want to look for some optimal quantal correlated equilibria, because as it turns out, for many games, it's beneficial for some signal for signal to look for optimal quantal correlated equilibrium, because when you can manipulate the behavior of players through signaling, you can achieve higher utilities than in quantal response equilibrium. Finally, to somehow well, we studied also the computational complexity of quantal correlated equilibrium, but this is a bit tricky question because most definitions of equilibria with quantal response players are very wide, and they encompass a wide range of different situations, and some of those could be trivial, which means that asking what is the complexity of computing any quantal correlated equilibrium is basically meaningless. But on the other hand, you can also construct in polynomial time some quantal generators such that from the corresponding quantal correlated equilibrium, you can find an epsilon Nash equilibrium, which basically means that the constant could be also pipette hard. So in the second part of our paper, we designed an algorithm which can actually compute the quantal correlated equilibrium. And for this, we used a homotopy algorithm. And homotopy algorithms are algorithms which take a set of a system of equations which is parameterized by a single parameter, which has such that on one side, on one end of the range of this parameter, you have a simple, trivial solution of the system, and then on the other end of the range, you have some desired solution. So, and exactly here we can use this property I talked about trivial quantal correlated equilibria, because we can use trivial quantal correlated equilibria as starting points of homotopy algorithms, and then as we increase the values of the homotopic parameters, we change the solution to the quantal correlated equilibrium, which we want to compute. And we didn't use the original system of equations which describe quantal correlated equilibrium. Instead, we did two modifications to ameliorate some numerical problems during tracing. So the first one was to eliminate the sum in the quantal response model using some reference action. This is a trick which you can see also in other fields, and it's quite common. But as you can see here, you can reduce this system to something like this. Still, the problem is that the quantal generators might be quite steep, which also causes some problems. So the second thing we did is that we eliminated the ratio, both ratios, which you can see here, by applying some substitutions similar to this one. Okay, and then to traverse the homotopy curve, we just use the standard predictor corrector methods, consisting of a simple Euler predictor, which just takes a point on the curve and uses a tangent to find the next point, which is often far from the homotopy curve. So then we use the Gauss-Newton corrector to get back on the curve consisting of the quantal correlated equilibria. So, so far, the algorithm I described, the homotopic one, assumed that the signaling distribution is being held constant. A more practical situation would be to look for some optimal signaling distribution, optimal equilibrium. But how do we find this? How do we approach this? Actually, it turns out that because the predictor corrector is differentiable, in case the criterion function is differentiable as well, during the tracing, we can shift the signaling distribution and also the whole homotopy using standard gradient ascent. Okay, like this, like you can see on the curve, like in each step of the tracing, we can somehow change the whole homotopy and as well as the signaling distribution. And the good thing is that we showed that Gauss-Newton still retains its guarantees. So even though we shift the whole problem, we can still converge to the proper point of the homotopy curve. Okay, so now we have an algorithm which can compute optimal quantal correlated equilibrium in different settings. And optimal signaling can be applied to many different situations. So for example, there are situations in like fighting misinformation, when you can send some signals which correspond to some fact-checking, for example. Or it can be applied to some cyber or physical security, where signals could be, for example, some deployed honeypots. Or some supply chain games where you could send signals to the traders to optimize the whole network. And in our empirical part, we used two domains to test this. The first one was exactly the supply chain games. And here we assume some interaction between suppliers and retailers over an area consisting of multiple territories. We assume that only the suppliers receive some signals from the authorities. those signals can be interpreted, for example, some taxation policies. And then the criterion was to optimize somehow to assure that there's some steady flow of products across the whole system. The second domain we used were just randomly generated games to assess the performance of the algorithm over a wide spectrum of different games. And here we assume that we want to minimize gene index. Okay, so here you can see some results which we achieved. We compared the homotopy algorithm to Baron, which is a standard state-of-the-art framework for computing solutions of nonlinear systems. Here you can see just, well, on the top row, you can see the results with just the tracing, not optimization yet, just the tracing. And basically the homotopy scales much better than if you would just use a generic solver. Now at the bottom row, there are some results with the overall optimization. Similarly, you can see sometimes of the homotopy algorithm of Baron, and then there's some difference delta in the quality of the solutions, which were found by homotopy with the gradient ascent and Baron, and those are quite negligible. So it basically suggests that the algorithm works quite well. Okay, so and that's basically it. That's everything I wanted to show you. So if you have any questions, I'll be very glad to answer those.
So we definitely have time for questions. Yeah, go ahead.
Yeah, actually, go back to the previous stuff. How did you initialize your homotopy map? Did you just initialize it with the distribution?
Oh yeah, exactly like this. Like for if you're talking about just the tracing, we started with the trivial Quantal Correlated equilibrium with just uniform strategies for each player, and then we just changed those. We deformed the whole system and its solution across the homotopy curve.
Yeah, so essentially like QIs go from constant to either linear, driving, whatever.
Yeah.
And then what is the homotopy there usually?
Sorry, once again.
Like what is the mapping from Q0 common T, I guess, to, right?
Wow.
You have to have like a family of mappings which go from
Oh, yeah, you mean like yeah.
What is the deformation?
Well, these are the quantal functions, like the generators. You start with the generators of the trivial Quantal Correlated equilibrium, and then you modify the generator such that you end up with the one you're looking for the solution for. Does it make sense?
But like there could be many generators, right?
Oh yeah, they can be many. Well, you mean the curve?
Yeah,
okay.
What curve are you actually using?
Oh, I see.
Yeah.
Well, there are theorems from the homotopy theory, which make some guarantees that there exists a unique curve along which you can travel to get from this trivial solution to the one that you want to get.
Yeah, I guess I was just curious if there's a fancy or slightly simpler. I'm familiar with the canonical representation, but I'm curious if there's slightly simpler ones that actually give you better convergence rates.
I see.
Right, because if they're simpler, you have to take larger steps.
I see.
Which means that you actually might
converge early.
And there's also weird stuff right? You can do, right? Change the Euler, integrate it into something else.
Oh yeah.
But anyways, yeah.
Okay, thanks. Anything else?
We have time for one more question.
Standard normal from games, corrected equilibrium could either be defined with a signal or saying what each player knows the quality of. Just say to each player, like the referee, that says to each player which action he should play.
Sorry.
In corrected equilibrium, you have two ways of defining it. Either with a signal, as we did, or like in normal from games, you have like a referee or someone that says to each player you should play this action. And then when you play this action, it's optimal for you to play this action.
Oh yeah, so this is the canonical representation. This is the difference between the canonical and the standard one.
Canonical representation here, if I say to each player you should play this quantal response, and then.
Yeah, well, this is what I was curious about, but I couldn't make this work like anyway. How to like recommend how to have a representation. This is one of the open problems actually, which I would like to explore in the near future. If we can have some equivalent of of the canonical representation where you'd be able to recommend some quantal action, like quantal strategies. But I tried to make this work somehow, but I wasn't able to. So I'm really not sure how to do this. But yeah, because this would be great, because such a representation would be much more efficient in coding the whole equilibrium instead of doing it the standard way. Because the standard way, this is a huge representation when you have the separate signal distribution and then optimal strategies of the players, which are conditioned on signals. This is like a huge representation, and then the utilities are nonlinear and everything like this. So something like a canonical representation, which is great because of the linear utilities and this kind of stuff, would be great for this.
All right, thank you again. So for the last talk, it's virtual, right? Do you want to set that up? Or?
No, I can do it all here. They have to share their screen and then I can.
Okay, is our last speaker here?